Now, I just wanted to try to do two things today. One is just again briefly summarize some general properties of band structures. And then after we do that, I'd like to tell you a bit more in detail how you can understand the optical properties of material, looking at the band structure of the material. Okay, so we have our usual phase diagram, E of k. And as we already argued, we may have several different possible situations. Let me draw a generic band structure like this, and there will be other bands above. Depending on the filling, we have, so once the band structure is given, so this is what we call band structure. Okay, the band structure is the collection of all the bands that result as a solution of the periodic Hamiltonian. And of course, different systems will have different band structures. Different band structures not only because the Brillouin zone will be different. If you're working with an FEC crystal, the Brillouin zone will have a BCC shape. If you're working with a simple cubic, the Brillouin zone will be a simple cubic unit cell. So there will be differences connected to the shape of the Brillouin zone first. But obviously, there will also be differences because the potential that characterizes the behavior of the electrons for different systems is different. And so the shape of these spaghetti-like plots will be different depending on with the system that you are considering. And we have seen two examples so far, two extremes of possible behavior in terms of band structure. The first example was the one-dimensional chain of hydrogen atoms, in which we assumed that the very good starting point was the atomic solutions. And all the rest, the fact that there was a solid around each atom, was treated as a perturbation. So this is really an extreme sort of starting point. You assume that the atomic solutions are good starting point, and you treat the presence of the other atoms as just as perturbation. Now, if you, so let me summarize here. So the first model was the hydrogen chain. Actually, this model is typically given a well-defined name. It's called tight binding model. Let me just a chain of hydrogens. We just solved it for a particular case, but I just want to give you some nomenclature, some naming. So this is what goes under the name of tight binding model. We solved it for a very specific case, a very simple case, but that's the spirit of the tight binding model. So tight binding model, essentially you assume that the atomic solutions, you do perturbation theory essentially, starting from atomic solutions. Now, if you do this, of course, you are somehow assuming that the overlaps, our delta E naught, our T's, are small numbers. They're not too big, because otherwise you're not allowed to do perturbation theory on top of that. Now, the consequence of this, of course, is that the width of the bands, if you use this model, right, which we, in the one-dimensional model that we developed, the chain of hydrogen atom was given by 2T, if you remember. Was it 2T or 4T? 2T. 2T, the total width, yeah. So the width of this band must typically be small. If it's too large, right, then the overall model may not be applicable any longer, of course, because you may be far from perturbation theory, essentially. So in some sense, I mean, the tight binding model works if atomic states are a good starting point, and as a consequence of that, the bands are typically narrow. They are very thin bands, typically separated by large energy gaps between one another. on the opposite side, we have the quasi-free electron model. I'm just summarizing things that we already discussed. I'm just discussing these models and comparing them. So we have the quasi-free electron model in which, on the other hand, we are actually starting from, we do perturbation theory, but starting from plane waves, so completely opposite starting point. We're assuming that the electrons don't even know about the presence of an underlying lattice, and we treat the lattice as a perturbation. Right? It's completely opposite. Here we assume that the lattice exists, and we treat the nearest neighbors as perturbation. Here we start from the assumption that the electrons don't even know about the existence of a lattice, and we treat the lattice as a perturbation. And of course, the consequence in terms of results is quite dramatic. Instead of having thin bands where the width is given by perturbation theory, here we have a continuum of states, the free electron states, these parabolas, in which the gaps now become perturbations. Right? The presence of the underlying lattice of the potential gives rise to thin gaps of energy in the system. All right? So they're really complementary. The two models are really complementary to one another. And to some extent, I mean, no system perhaps behaves entirely like this or entirely like this. Real systems generally, I mean, you can understand them. You can understand qualitatively their properties using one of the two models. But if you want to do real calculations, you have to be more accurate. You have to do well, either push these approximations to the next stage, or you have to use a combination of the two approximations to deal with systems. A typical example is transition metals. I'm sure you know the periodic table, right? You have on the left side, you have the alkalis, the valence is 1 or 2, and those systems are, I mean, qualitatively described pretty well by the quasi-free electron model. Qualitatively, of course, not quantitatively. And actually, if you're in the first column, this is not just qualitative, it's actually almost quantitative because of, you remember this fact that if you have a 1 electron per cell, you're filling only the bottom of the band, and the bottom of the band doesn't really see what's happening at the edges of the Brillouin zone, so it's actually a good approximation. So if we are, say, in the first, second column, the alkalis, this is not a bad description. On the other hand, on the other side of the periodic table, you are in the rare gases. Rare gases, the atomic orbitals are extremely tightly bound. By the way, tight binding precisely means this. The electrons are tightly bound to the atoms. Okay, so this is actually a very good starting point to describe the the band structure of a rare gas, for example, whatever that means, because crystallizing a rare gas is very difficult. And so there are very few experiments being done on crystals of rare gases. In fact, helium itself never crystallizes at ambient conditions because the interaction is too weak that there's no chance for them to form a crystal. But xenon, argon, and all the other crystals, if you go sufficiently low in temperature, they do crystallize. But these are really exceptions. I mean, they're not systems that you see around yourself. So I would treat them as really as exceptions. So this is good, of course, for the rare gases. Let's move to close to the center of the periodic table. Let's do it. Let's go from the right. So if we go from the right, you enter into this category of systems, the central ones being carbon, silicon, germanium, valence 4, and then you have also valence 3 and valence 5 and valence 6 as well. So these are systems for which the atomic model works reasonably well qualitatively, of course. So these are the elements of group, let's say, 3, 4, 5, well, also 6 and 7 in principle. I mean, we're talking about the moving from rare gases all the way to the third column of the periodic table. Not that they, I mean, describe quantitatively these systems, but qualitatively they describe quite well. Now, surprisingly, you try to model these systems also with plane waves, and they're not that bad either. if you look at the band structure of silicon, for example, silicon has been historically one of the systems which has been most studied in the literature because of, obviously, for electronic purposes. And so people have tried to calculate the band structure of silicon from a tight binding model. It comes out reasonably qualitatively well. If you do it with quasi-free electrons, it comes out qualitatively well as well, but not quantitatively, neither approximation, right? So this is also not so bad, I mean, in principle, for, say, group 3 to group 7. Then we enter into this very interesting territory made of the transition metals, which are in between, right? The left and the right side of the periodic table. Now, transition metals are very peculiar because transition metals typically correspond to a partial filling of Nd orbitals and n+1 s orbitals. The typical electronic shell of a transition metal is n principal quantum number d something and n+1 s something, okay? So you're filling actually two shells at the same time, two atomic shells at the same time. Yeah, I'm not able to give you an example now of my, but anyways, I mean, you're filling partially this and partially also the S, say, 3D iron, for example, would be 3D 9, 4S 1 or 2, I forget now. Anyway, so you're partially filling the D shell, 3D shell, and partially the 4S. That's the first row. You go to the second one, and it's 4D something 5S, and so on and so forth. The next one will be 5D 6S. Now, d orbitals tend to be very localized. So d orbitals are typically described quite well by the tight binding model. S orbitals, unfortunately, they behave like the s orbitals of the alkali atoms. So they're very delocalized. So transition metals are a somehow tricky system because different categories of orbitals behave in a different way. So none of the two approximations works for both, and in principle you should be using the tight binding to describe the d orbitals and the free electron model to describe the s orbitals. In fact, if you look at the band structure of transition metals, you'll find, I didn't bring anything, but I would advise you to take a look at band structures in books. If you look at the band structure of a transition metal, you see a very narrow and dense set of lines which are very concentrated in a very narrow range of energy and very flat, and these are the d orbitals because they are described by the tight binding model. And then you see a much broader spectrum of almost quasi-free electron, almost free electron bands, which arise from the s electrons. So it's a combination of the two. It's a mixture between free electron behavior and localized behavior that characterizes the electronic structure of transition metals. So transition metals are somehow, they require both in order to be described properly. There's no way you can describe with one or the other one of the two approaches. Oh, I forgot to mention that those of you with a chemistry background, this model here is what chemists call LCAO, linear combination of atomic orbitals. Those of you who have some chemistry background might realize that this is formally the same as the LCAO, or the class of LCAO models. So linear combinations of atomic orbitals. You start from atomic orbitals as the unperturbed states, and then you do linear combinations of them. LCAO in chemistry. This is, of course, analog in chemistry of plane waves. In chemistry, everything is localized. All right. So this is just a general discussion about two extremes, once again, two extremes. Nice models because they allow us to get some qualitative results easily. if you want to do more accurate calculations of band structures, forget about this, forget about this. You have to do more sophisticated calculations. The way you do them is really depends on the system, but let me just mention briefly that if you really want to be more accurate, and nowadays, unfortunately, you have to, if you want to be quantitative, you have to be accurate, and there are models that allow you to be more accurate than these two simple models that we teach in class. Let me just give you a flavor of the way you do it. In the tight binding model, essentially what you do, as we already discussed, by the way, is you introduce more atomic orbitals. So introduce in your expansion all the possible atomic orbitals centered at each given site. Of course, the problem becomes much, much bigger from a numerical point of view. You have to diagonalize large matrices, but I mean, nowadays with computers you can do it. So in principle, you can push the tight binding model to become more and more accurate by just adding more states in your linear combination. Okay? As soon as, I mean, your wave function becomes completely described by this linear combination of atomic orbitals, then you have reached convergence. So there is a systematic way, let me put it this way. There is a systematic way to improve the tight binding model by just increasing the size of the basis set of your, and of course also extending the range at which you keep these overlaps, because in our model we kept only nearest neighbors, but you can of course keep second nearest neighbors, third nearest neighbors, and so on and so forth. The more you extend your range of overlaps that you keep in the calculation, the more your calculation is going to be accurate. You're going to neglect less things from your problem. So there are systematic ways to improve this and to make it more and more accurate in principle. Same, of course, for the quasi-free electron model. The underlying principle is that both the atomic orbitals and the plane waves are in principle a complete basis set. Okay? So if you expand your wave function in a sufficiently large number of elements in your basis set, then your calculation can be made arbitrarily accurate. So here you do it by adding more atomic orbitals in your basis set. Here you do it by adding more plane waves to the basis set. For example, this splitting that we obtained last time, that was obtained based on the fact that we limited our discussion to the 2x2 problem related to the degeneracy. We identified the two plane waves that were giving rise to this degeneracy, and we work on this 2x2 subset. But in principle, nobody prevents us from taking the full set of plane waves and expanding our wave function as a linear combination of an arbitrary number of plane waves. Not just two, not just one, an arbitrary number. Because plane waves are a complete basis set, we can just push the accuracy of this model to whatever level of accuracy we want by just adding more plane waves in the wave function. Okay? So this is just to say, yes?
Well, in the quasi-free electron model, we treat the lattice as a perturbation, right?
Right. So the concept is now, so your question is now, in this model, we are treating the lattice as a perturbation. So the question is now, suppose the lattice is no longer a perturbation now. What can you do within the free electron model? Well, you can still say that you expand your wave function as a linear combination of an arbitrary number of plane waves. Okay? So you don't use perturbation theory any longer, but you still use the same basis set to expand your wave function. And the potential, of course, is arbitrarily large, can be arbitrarily large. And you just essentially remove this perturbation theory part in your problem. And of course, you have to now build in a combination with arbitrary number of plane waves. Same here. You don't treat this any longer with perturbation theory, and therefore you have to put an arbitrary large number of atomic orbitals in your basis set, because the interaction now can be of arbitrary strength between nearest neighbors. So this is just to say that both models, they have the virtue of being simple models if you use perturbation theory, models that you can work out the solutions quite easily, at least in a lecture. But there are also models that can be extended by just including more elements in the basis set and therefore going beyond perturbation theory to obtain accurate results numerically. I mean, physically, quantitatively good results that you can, say, make predictions out of it, at least. Not just plotting qualitative plots like we have done so far in class. Okay, so end of the digression about about these two models. Now I would like to discuss now again general properties of band structures. I will probably repeat things that we already discussed in class, but I just wanted to fix the concepts before we move ahead. So if we have an arbitrary band structure like this, let's forget about whether this has been obtained by tight binding or free electron. Yes, you have a question. Practical applications of those models. Everything has a practical application in this field. That is, the overall goal of these theories is to be able to predict or to explain the properties of real materials based on our theories. Okay, so there are some aspects, some physical properties that are described qualitatively well by these two models. There are some other aspects which require more sophisticated, not sophisticated, but just more accurate solutions, not the ones, I mean, you'll never, if you do the chain of hydrogen atoms, you'll never be able to study an FCC packing of tungsten atoms, right? You would need to expand the model in order to include the s orbitals, the d orbitals, and so on and so forth. So what I gave you is just a flavor of what the methods look like, and we solved them in a very specific, actually the simplest cases. But you just need to extend these models a bit further, and then you'll be able to make real predictions about properties of materials. You just need to apply these methods to, with the appropriate say, ingredients, but essentially the spirit of the method is what we discussed in class. So the answer to this is, yes, if you do it carefully, of course, not the simple models that we have done in class, but if you take these models and you push them with including more orbitals, blah, 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 yes, you can predict the properties like what is the band structure of aluminum, for example, or what are the electronic states in glass, and what are the, and a number of other things. So they are useful, yes. Yes.
I saw, I mean, if, for instance, when we may have even number of electrons, and then sometimes, okay, is it how the temperature affects, I saw something holds.
I'll come back to this question, the effect of temperature, next time, I think, when we discuss semiconductors. If you allow me, we'll come back to that later on. But so far, you're right. Okay, so probably it's good to mention it now. So far, we have been completely neglecting the effects of temperature. In other words, we are assuming that, say, if there is a Fermi level here, all these states are filled, and all the states above the Fermi level are empty. You certainly know that statistical mechanics does not allow this kind of behavior, right? That there is actually a continuum of states, and the occupation of the states must obey Fermi-Dirac statistics, right? So in some sense, assuming that I fill completely the states up to this point and I leave all the other ones empty is like assuming that my temperature in the Fermi-Dirac distribution is 0, right? Because if the temperature is 0, Fermi-Dirac distribution becomes a step function. So I can fill all the states up to a given point and 0 elsewhere. But since you have heard about Fermi-Dirac distributions, you probably, I mean, you can already guess that at finite temperature, there will be a small number of electrons that occupy excited states, and of course there will be a small depletion, right? There will be less than 2 electrons per state here because they will be thermally excited into the excited state. So there will be an excitation due to temperature, essentially, due to the fact that the Fermi-Dirac distribution is not a step function, but it's a smooth function, so it goes to 0 in a smooth way. So you go from 2, occupation 2 here, 2, 2, 2, 2, 1.9, 1.8, 1, 0.5, 0, 0, 0, 0, 0, right? If I want to show the occupation number, that is the amount of electrons that are filling each one of these states along the band. Now the question, of course, since we are in business, the question is how broad is the range of energies where this takes place, where this transition from 2 to 0 takes place. Question for you. KBT, right? If I now plot f of E as a function of E, Fermi-Dirac distribution, this is what I call EF. You might have called it chemical potential. I don't know what kind of notation you use. EF, do you use EF? Okay, fine, sorry. And the broadening here is given by KBT. So if I now plot, let me actually plot here f of E here. So it's going to be 2. This is the Fermi level. Then it goes to 0 like this, right? Actually, let me use the yellow color. Right? Is that clear? I'm now plotting EF versus E. That's the Fermi energy. So here the occupation is 2, and here it goes to 0. So this is the occupation of state at the given energy E. Now, at the Fermi level, it's exactly 1, right? So it must be 1 here. The occupation of this state must be 1 by definition. And of course, the width of this is, as we just said, KBT. Now, what is the value of KBT in electron volts, for example, at room temperature? Suppose we're at room temperature. What is the value of KBT at room temperature in electron volts? In electron volts because, well, in electron volts because we know that band structures, the typical scale of a band structure is of the order of electron volts, right? The scale of energy is that of the atomic problem, so it must be electron volts. Few electron volts, 3, 10, 20, so on, something like that, right? So we know that the scale of energy of a band structure is electron volts. What is the scale of energy of KBT at room conditions?
In the order of Rydberg.
This is the kind of numbers that if you want to become a solid-state physicist, you have to remember by heart, okay? Actually, even if you are become a statistical mechanics person, you can forget about it only if you become a particle physicist. Okay? What is the value of KBT at room temperature?
13 times 20.
There are two ways to remember it. At room temperature, of course. T equals to 300 Kelvin. Either you remember it in this way, it's 25 milli-electron volts. Or another way to remember it, if you are lazy, you won't want to remember two numbers, you just want to remember one, it's 1/40th of an electron volt. Okay? If you wish, you can prepare a golden plate and put it on top of your desk there. This is a very important number for a solid-state physicist. KBT at room conditions is 25 millivolts, or 1/40th of an electron volt. Of course, approximately, right? It's not exactly that. Approximately that. With some commas and some other digits, of course, after the comma. Now, what is the consequence of this, at room temperature at least? This width is 25 milli-electron volts. The typical band structure has a width of the order of electron volts. This width here is very small. So the range of energy in which the occupation number goes from 2 to 0, crossing the Fermi energy, is very narrow. It's almost a step function. Okay, as far as the band structure is concerned. Of course, if you look with the microscope, then of course you'll see a distribution. But the point is that the width of this decay from 2 to 0 across the Fermi level takes place in an energy range which is very small compared to the typical width of a band. So this is like a step function as far as a solid-state physicist is concerned. Okay, so we can actually forget about, or at least, no, not forget about it. We can, for a large number of purposes, we can forget about the fact that we deal with a finite temperature. We can assume that the system is at 0 temperature. There's no major difference with respect to the band structure at 0 temperature or at room temperature. Scale of energy is much higher for the band structure compared to KBT. I'll come back to this one of the next lectures when we discuss semiconductors, okay? So for the time being, let me just assume that the temperature is 0 and that we have states below the Fermi level completely filled and states above the Fermi level completely empty. End of the digression about temperature, but we'll come back to that later on. Okay, so, we already discussed almost everything. I just want to refresh some ideas. So what is the Fermi energy? Fermi energy is the energy below which all states are filled and above which all states are empty, at 0 temperature at least. The Fermi vector, or the Fermi point in one dimension, is the set of points that correspond to crossings of the Fermi energy and the band structure. So the points corresponding to states lying exactly at the Fermi energy. So this will be a set of points. In one dimension, it will only be 2 points. In 2 dimensions, it will be a line or a set of lines. In 3 dimensions, it will be a surface or a set of surfaces, 2-dimensional surfaces. We already discussed, filling 2 electrons per cell means you fill the full band. Odd number of electrons means that you fill at least one of these bands partially, so we have certainly a metal. All these things, I guess, I don't want to repeat them. We discussed them, and these are true in general. In the remaining half an hour, I'd like to discuss briefly optical properties. How do we understand the optical properties of a material? Yes, quick one, because otherwise I won't.
Okay, when we see C, the energy is positive, right?
The energy?
Is positive.
Yes and no. Depends where you set your 0. We already discussed this several times, right? That 0 is somewhat arbitrary. It depends. We wish to put the 0 at the bottom of your last band, for example. Or you may wish to put the 0 at the vacuum level. Then all this will have to be negative. Some people set the Fermi energy to 0. It's arbitrary. It depends. You have to tell me what is the reference, and I will plot the band structure according to your reference.
Yeah, because we start with plane wave and...
Right. If you start with plane waves, it becomes natural to set the 0 here, of course, at the bottom of the band.
Yeah, then the energy is positive means it means the electron is not bound.
Yeah, correct. The fact that the energy is positive means that the electron is free, but that's not the case because the electron will be still confined within the box made of the surfaces of the material, right? The electron certainly will not be able to escape from the material because there will be an electrostatic barrier at the edges at the surface of the material. So if you compare the energies with respect to the vacuum energy outside, then the whole thing is actually negative. The electron is confined inside the material. Otherwise, if free electrons had a positive energy, there would be free electrons escaping the materials at every time, right? They don't, because they are actually confined to be within the material by the fact that the overall energy inside the material is actually negative below the vacuum. So it's up to, up to you, and to whoever wants to tell me what is the actual reference, and I will plot the band structure according to that reference. Optical properties. All right, so we are talking about this kind of experiments. So we have our material and we have light photons hitting a material, and we want to know what's happening to these photons, essentially. Okay? And we have our solid, And our solids, we suppose we know everything. We know the band structure. We've been good enough to come out with a good model of the band structure. And we want to be able to predict what will be the outcome of this light hitting the material and combined with our knowledge of the band structure. All right, so we have photons arriving here. So photons are, from a quantum point of view, are particles which carry an energy and a momentum as well. There are these photons that will hit some of your electrons, right? So we'll hit, for example, this electron here. And if the electron absorbs the photon, it will acquire an energy which is equal to the energy of the photon, obviously. Okay? Have you seen absorption in atoms? Are you familiar with the fact that you can excite electrons from one state to another one, and the energy must be quantized due to the difference between the energy levels, right? So you're all familiar with these statements. Whenever you have light coming to a material, there will be absorption at an energy corresponding to two states, between two states, when the difference in energy between the two states corresponds to the energy of the photon, okay? So the difference with respect to atomic physics now is that instead of having single discrete states in the atom, we now have a continuum of states, both continuum of field states and a continuum of excited states. These are excited states, these are excited states, these are the field states. Okay? So in principle, there is a photon, hits this electron, and this electron can be excited everywhere, here, here, here. There are infinitely many possibilities. Now, I'm going to make a statement which is very qualitative, not quantitative. It's not formally easy to prove. But I will make the following statement. The photon carries not only an energy, but also a momentum. Okay? The momentum of the photon, let me use the word Q, is 2 pi over lambda, right? So it carries both an energy as well as a momentum, which is 2 pi over the wavelength of the light. Now, even though I've been always trying to brainwash you and convince you that K is not a good quantum number and is not the momentum, I now need to relax a little bit my statements and say that, well, when you excite an electron from here to one of these states, you have to make sure that the energy corresponds to the energy of the photon, but you have to make sure also that the momentum that the electron acquires, which is Q, corresponds to the change in K. So you have two constraints that you have to use if you want to study the absorption of an electron, the absorption of a photon by an electron. You have to make sure that this condition is satisfied, that there is a state at an energy equal to h bar omega. But that's, I mean, with a few exceptions, is always true, because if the photon energy is, say, this one, right? If this is the photon energy, for example, there will always be two states which have that difference in energy. Because you have a continuum of states, you're not like in the atom that you can have absorption only when the photon has a particular energy, because you only have discrete levels. In a solid, you have a continuum of states. So either you're so unlucky that your excitation energy is in this gap, and of course here there are no states available, or say 80% of the cases, you will have the possibility to hit two states with that energy if you have a continuum. However, there is a second condition. So the first condition is on the energy, but there is also a second condition on the momentum. The change of K, and that's again a very qualitative statement, because I always told you that K carries no physical meaning. Now I have to make an exception and tell you that K actually does carry a physical meaning. Anyway, the change in K must equal the momentum of the photon. That is, it's like an elastic collision. You gain an energy which is given by the photon, and you gain a momentum, which is the momentum of the photon for an electron. So the question is, what is the typical value of this Q here in a typical band structure? Now, I'm sure you're familiar with the fact that light, ordinary light at least, let's talk about visible light for the time being. This is the, let's say, when we talk about optical properties, we generally speaking talk about visible light or close to visible light. So lambda for visible light, do you have an idea of what is lambda for visible light? Roughly, orders of magnitude. 500 nanometers, very good. Plus or minus 200 nanometers. Okay, you go from 700 nanometers to 300 nanometers. So the typical order of magnitude is of the order of 500 nanometers or 5,000 angstroms, depending on your. What is the typical? So this Q is 2 pi over 500 nanometers. What is the typical size of the Brillouin zone? The typical size of the Brillouin zone is of the order 2 pi over atomic distances. But atomic distances are 1 nanometer, even less fractions of nanometers. So this Q here is certainly much, much smaller than 2 pi over A, which is the size of the Brillouin zone. Right? So in other words, the momentum carried by a photon is negligible on the scale of our Brillouin zone, because the size of the Brillouin zone is characterized by 2 pi over A, and A is very small compared to the wavelength of light. So this Q disappears in this scale. It's nothing. It's a tiny, tiny object on the scale of our Brillouin zone. All right? Consequence of this is that I can actually neglect about the conservation of momentum. I can say, well, my electron will be excited by essentially keeping its K value the same. Because if there is a change, this change is of the order of Q, but Q is negligible. So the momentum that the electron can acquire is essentially zero. It's very small. So the electron can only go up vertically. So this is not allowed. Not allowed. The only possible excitations for the electron is excitations that go straight, vertical. So this is an important statement, which you will find very frequently in the literature. Only vertical, whatever that means, right? We know what it means. Vertical in the band structure. They can only go straight up. Transitions are allowed. Of course, by optical photons. By photons of optical wavelength. Okay, so if you have light, ordinary light shining on a material, you can excite electrons. It will excite electrons in your material, but it will only excite electrons vertically. It will not be able to excite electrons at different places in the Brillouin zone. So let me now redo this plot, because otherwise this is becoming too messy. So I have my band structure here. I have another band structure here. I have, for example, well, let me begin by treating an insulator. So let me begin by saying now I have a system with, let me discuss the general properties of an insulator now. Well, in an insulator, for example, I'm filling completely this band, and all the rest is empty. Okay? And what I'm going to do now is to try and plot the absorption coefficient What is the absorption coefficient? It's the amount of photons that will be absorbed at the typical energy of the photons. So now I'm trying to think of an experiment in which I have light that I can change their frequency. So I have a source of light that I can tune, where I can tune the frequency of the light, and I measure how much photons are absorbed at every frequency by changing the frequency, okay? But within some constants, this is what we call the absorption coefficient, how much photons are absorbed by the system at any given frequency. Suppose we start with a very small frequency. This very small frequency means small photon energy. So I can excite electrons, and I have to go up. That's the only possibility I have. And I have to go vertical. I won't be able to find any excited state that matches these excitations. So I won't be able to excite any electron in my system. So light will just go through unperturbed, no absorption. The absorption coefficient will be 0. No absorption at the beginning. At some point, the energy will reach this value, right? H bar omega will reach this value. At this point, I will start absorbing, because this electron, it will be possible to excite it in the first available excited state. For all the other ones, nothing will happen, right? Because for all the other ones, there will be no available state. But for this one, there will be one. So there will be a critical value of H bar omega, right? After which, I will start seeing some absorption. If I continue, of course, I will be able to have this electron now absorbing. This one no longer, because if the arrow is too long, this electron will not have any excited state available. But there will be another one close by that will absorb. And all the other ones will do nothing. Well, there will be another one here as well, of course. So you immediately see that if I increase my H bar omega, I will be able to find a place somewhere in my band structure where the height of the stick will match exactly the difference in energy, right? Whatever is the length of the stick. If the length of the stick is, say, my fingers, it will be here. If it's a bit more, it will be a bit here, right? So there will be a range of frequencies for which there will be absorption. The photons will be absorbed by the system. That is, there are pairs of states whose the energy difference of which coincides exactly with the photon. Then there will be a point, say, when I exceed this energy, right? If the energy becomes bigger than this, of course, there will be no way to excite from here to here. So it will have to go back to 0, perhaps. But then there might be other bands. So it will restart again. Or perhaps there may be bands that start here. And then it will never vanish, because there will always be, if this is longer than this, there will be somewhere else a place in which I absorb from here to here, right? So what's happened later on, it's really a matter of details of the band structure. It can either go to 0 and then start again, or it will continue like this. The important point, however, is that there is a critical value here of the energy, which I call the energy gap, because it is indeed the energy gap. It's the minimum excitation energy in my system, below which there is no absorption, and above which I start having absorption. All right. Now, suppose, let's try to think at possible values of the energy gap. Suppose the energy gap, I need to place somewhere here the visible spectrum. That is, I need to place, here I'm going from 0 in principle to infinity for H bar omega. But let me put the visible spectrum somewhere. Let me see if I have a red. Well, a green. I can use the green. There is no blue. Say, somewhere here, there will be the visible spectrum. Visible spectrum goes from roughly from roughly from 1.5 electron volts to I forget now, 2.3 electron volts roughly. Okay, so that's the visible range. So this is the range of frequencies which we see with our eyes.
Sir?
Yes?
Okay. At a given omega,
Yes?
a single, we have a single electron that absorbs a single.
Yes,
right?
so at a given omega, yes, we have a single, or we have all the electrons for which this coefficient is exactly matched, which is can be a line, can be a, it's like the Fermi surface, it can be a...
Why we have, it should be, I think, constant and after...
Okay, good point. So you're arguing, I mean, why what is the height of this? Well, this is because there is not only the matching energy condition, but it's also the transition matrix element that we need to calculate in principle. You might remember Fermi's golden rule. Do you? Right, so the absorption coefficient or the transition probability is proportional. I mean, there is constraint is that the difference in energy must be matched, but there is also a factor in front of it, which is the transition matrix element between the initial state, the final state, and the dipole operator or the transition operator for the...
So this is not exactly the number of photons.
Exactly. So this is not exactly the number of electrons, the number of photons. This height is determined by the transition matrix element. Yes.
And here we have K minus K symmetry.
Yes. So they always have. You always, if you have a transition at a given point, you always have a transition also at the other point, of course.
And then at a time we can have only one transition, right? One excitation. So which one will the
well, I mean, this is okay. We're now talking about quantum mechanics. So, from a if you follow the probabilistic picture, it's you have to have a large number of photons, and the probability that one will excite one or the other one will be 1/2. At the end of the day, you will have absorption from both. I mean, 50% probability one, 50% probability the other one. Okay.
Because now we are increasing the frequency.
Yes.
And then at that time, one electron will absorb and will jump. And then when we pass, I'll think about it.
Okay, think about it. And now what I wanted to discuss, the final thing I want to discuss is where is the visible range? Because I would like you to understand what are the consequences of this spectrum on our ability to see an object or to see through an object. Okay? Now, there are several possibilities now. If the visible range is all below the gap of the system, in other words, if there are, say, three possibilities. The first possibility is that the visible range is all below the energy gap. Or in other words, the energy gap is larger than 3 electron volts. So let me now assume that my gap, it's an insulator, and the energy gap is large, is of the order of 3 electron volts, in such a way that the visible range lies completely below the gap of the system. Okay, so the visible range is here. What's happening here? If I look at my system with my eyes, all the frequencies corresponding to visible lines, none of them will be absorbed. All right? So the system must be transparent. All right? So if the gap of my system is larger than violet, whatever it is, 3 electron volts, I will see through that material. Glass is an example. The energy gap of glass is of the order of 7, 8 electron volts. There are not so many materials that have this property, by the way, because you require the gap to be very large, to be larger than 3 electron volts, and only a few materials have this property. Glass is one, quartz, obviously, which is similar to glass. Diamond is another example. Some kinds of plastics, say polyethylene, for example, is, well, PVC. Seen here a bottle of water. So there are two materials here that have this property. One is the plastics, PVC. PVC has a gap of about 6, 8 electron volts. Water. The gap of water is 8 electron volts. Okay, so in order to see through, your material must have a gap which is larger than 3 electron volts. You take aluminum, the gap is certainly below, because you don't see through aluminum. You don't see through, say, plastics. You don't see through wood. You don't see through concrete. That means the band gap must be smaller than that. Okay? Now, there is another possibility. Let me put it as 3 here, and then I'll discuss the 2 later on, is that the gap is actually entirely below the visible range. Okay? So now the visible range is here. The gap is completely below the visible range. What's happening here? Do I see through this material or not? I can only see these frequencies, right? These frequencies, all of them are absorbed, right? All of them, with no exception. So if I shine light through my material and I look at it after, behind it, I won't see anything. I won't see any photons. So that's precisely what I mean by a material which is not transparent. Okay, like most materials actually we know, they are not transparent. Okay, so this is transparent, and this is certainly not transparent. Some people call it opaque. Let me just say not transparent. But there is another case which is actually interesting, and this is where the gap is in between the visible range. That's actually very interesting, because can you guess what's happening here? Right. Some of the light will pass through. Some other light will not. Now, light that goes through is actually the one with the lowest energy, right? For sure. And light that doesn't go through is the one with the highest energy. Now, I'm sure you know the colors, right? The colors start from red, yellow, green, blue, violet, right? So if you look at the material where the gap is, say, 2 electron volts, for example, how will it look like? You take a material, you look through it, you put a light behind it, and you look at it. What will it look like?